Insertion in red-black trees. Red-black trees are self-balancing binary search trees that maintain optimal search performance through color-based balancing. Understanding how insertion works is essential because inserting a new node can temporarily violate these balancing properties. In this presentation, we explore how red-black trees restore balance after insertion. The challenge of insertion. The problem. When we insert a new node into a red-black tree, we risk violating the fundamental balancing properties that make these trees so efficient. Simple insertion isn't enough because it can disturb the tree structure. Therefore, we need sophisticated fix-up operations to restore balance. Why it matters? Without proper balancing, the tree could degenerate into a linked list, destroying the O(log n) performance guarantee. The insertion algorithm ensures that we maintain logarithmic height through strategic recoloring and rotations. Red-black tree properties recap. Rule 1. Node colors. Every node in a red-black tree is either red or black. No other colors are allowed, which keeps the structure simple and easy to reason about. Rule 2. Root property. The root node must always be black. This provides a stable foundation and ensures consistency at the top of the tree. Rule 3. Leaf nodes. All nil or null leaf nodes are considered black. This simplifies our algorithmic reasoning and helps maintain uniform black height across the tree. Critical balancing rules. Rule 4. No consecutive reds. In a red-black tree, a red node must never have a red child. This rule prevents the formation of red chains, which would unbalance the tree and increase its height. During insertion, this is the rule that is violated most often and therefore needs immediate correction. Rule 5. Equal black heights. Every path from any node to its descendant nil nodes must contain the same number of black nodes. This rule guarantees that the tree remains approximately balanced across all branches. The insertion algorithm. Step 1. Standard BST insertion. First, we insert the new node. Using standard binary search tree logic, we compare values and traverse either left or right until we find the correct position. Step 2. Color the new node red. The newly inserted node is always colored red. This choice minimizes violations because adding a red node does not affect the black height of the tree. Step 3. Fix violations. If the parent of the new node is also red, Rule 4 is violated. To restore balance, we apply fix-up operations using rotations and recoloring. Why insert as red? Inserting a node as red is a strategic decision. It preserves Rule 5, the equal black height property, because no black nodes are added to any path. The only possible violation is Rule 4, which involves consecutive red nodes. This violation is easier to fix locally using rotations and recoloring. Key insight. Violating Rule 4 is preferable to violating Rule 5 because fixing black height violations would require global tree restructuring. Fix-up cases overview. After insertion, the fix-up algorithm examines the color of the uncle node, which is the parent's sibling. Based on the uncle's color, one of three cases applies. Case 1. Uncle is red. If the uncle is red, we recolor the parent, uncle, and grandparent. This case is simple and efficient and does not require any rotations. Case 2. Uncle is black triangle. If the uncle is black and the nodes form a triangle shape, we perform a rotation to convert the structure into a line. This is a preparatory step. Case 3. Uncle is black line. If the uncle is black and the nodes form a straight line, we perform a rotation and recoloring to fully resolve the violation. Case 1. When uncle is red. Initial state. The grandparent is black. Both the parent and uncle are red. The newly inserted node is also red. Recolor operation. We flip the colors. The parent and uncle become black, and the grandparent becomes red. Result. The local violation is fixed. However, the grandparent may now violate Rule 4 with its parent. So we continue checking upward. Case 2. When uncle is black and form like triangle. Initial state. The grandparent is black. The parent and newly inserted node are red, forming a triangle configuration. The uncle is black. Rotation operation. We perform a rotation on the parent node. This rotation reorients the local subtree and transforms the triangle into a straight line configuration. Result. The tree is now prepared for the case 3 fix-up. This is an intermediate step, not the final solution. Case 3. When uncle is black formed like line. Initial state. The grandparent is black. The parent and newly inserted node are red, forming a straight line with the grandparent. The uncle is black. Rotation and recolor. We perform a rotation on the grandparent node to break the straight line structure. Then we recolor. The parent becomes black and the grandparent becomes red. Result. The violation is fully resolved. All red-black tree properties are restored, and no further upward iteration is required. Insertion code implementation. In this we will see the main insert function used in the red-black tree. The method starts with public void insert, int data. Public is access specifier, insert is the function name, data is the argument passed and its type is integer. This function is called whenever we want to insert a new value into the tree. Inside the method, we first check if this dot root is equal to null. This condition checks whether the tree is empty. If the tree is empty, a new node is created using the given data and assigned as the root node. Immediately after that, the root node's color is set to black. This is required because one of the red-black tree rules states that the root must always be black. If the tree is not empty, the code moves to the else block. Here, the insert operation is passed to the helper function insert help. This helper function performs standard BST insertion and then applies recoloring and rotations to fix any red-black tree violations. Finally, the updated root is returned and stored back in this .root. This code ensures that every insertion maintains both the binary search tree property and all red-black tree balancing rules. Summary of insertion algorithm. After every insertion, The red-black tree properties are carefully restored. First, the node is inserted using BST logic and colored red. If the node becomes the root, it is recolored black. If the uncle is red, recoloring is performed. If the uncle is black, appropriate rotations and recoloring are applied. Finally, the root of the tree is ensured to be black. This process guarantees that the tree maintains O log n performance after every insertion.